In this class, we're going to take a look at a geometric sequence. So unlike an arithmetic sequence where each term is generated by adding or subtracting a number, in a geometric sequence, each term is generated by multiplying by a number. So for this example here, we start with the first term of 3 and we just multiply by 2 every time, and the numbers just keep getting bigger and bigger. In the case of this one here, we're multiplying by 1/2 every time, so still multiplying by some factor, but the factor just happens to be a fraction type number. So we're making the numbers smaller every time, and that would carry on indefinitely as well. So we want to think about these in slightly more general terms so we can start to gain some insight into geometric sequences and start to generate some rules. So this, you can see, is going to get smaller and smaller and smaller and smaller towards 0, but it can never pass over 0 because you're multiplying by 1/2, which is a positive number. So there's no way to multiply a positive number by another positive number and get a negative. So there's no way that this can ever go beyond 0, but it is going to, you're effectively halving the number every time. So you're bridging the gap between this number and 0 by halving it and halving it and halving it. So you're going to get closer to 0. So we can see clearly that that one is going to tend to 0. And we say then that this guy here has got a limit, and then the limit equals 0. So this is an example of a geometric sequence which converges, and it converges to the limit of 0. This guy up here, on the other hand, is doubling every time. So each of the terms are twice the previous term, 2 times the previous term. That's just going to get bigger and bigger and bigger. So that's going to diverge to positive infinity. Okay, so this guy's got no limit, no number that it's getting closer to. So it's got no limit and it diverges. So it's possible to get both types of behavior with a geometric sequence. So just to try and generalize these a little, let's call the first term in our generic sequence A, and let's call the multiplying number. So here we're multiplying by 2, so multiply by 2, multiply by 2. Let's call that multiplication number R, and R stands for ratio. It's a common ratio. So A is the first term, R is a common ratio. So to get from the first term to the second term, we multiply by that ratio. So multiply A by R, and you get AR. Multiply the second term by R, and you get AR times R, which would be AR squared. And that is just going to carry on. Then you're going to get AR cubed, etc., etc. That's just going to stick with that pattern of multiplying by that common ratio every time. But remember that with these sequences, we are always interested in connecting not only the terms to each other, but also the terms to what we call like a placeholder number. So this is the first term, second term, third term. So we also want to think about them in that way. What is the connection between 1 and 10, 2 and 5? How can we build up that relationship? Well, here, between each term, we're just multiplying by R. And if we put on those placeholder numbers, we can see that the power on the R is always going to be 1 less than the placeholder number. And if we call the placeholder number n, which is how we normally notate that, then this is a power of 1, which is 1 less than 2. This is a power of 2, which is 1 less than 3. It's always going to be 1 less because the power on the R represents the number of gaps between the terms. So here you've got 1 gap, but if you go up to the third term, 1, 2, 3 terms, you've got 2 gaps. If you included 4 terms, then you've got 3 gaps. So the number of gaps basically is representing the power, and it's 1 less than the number in the sense of the placeholder. So pulling that all together, what that means is that we can derive a general formula just by saying, well, each term is going to have an A in it, which they all have, and it's going to have an R in it. And then the power that goes on the R is just 1 less than the n value. So it's AR to the n minus 1. And that's basically our formula for generating any term in the sequence. So we could call that our A sub n. So you can generate a generic term A sub n by using that formula. Because one of the things we want to do is, let's say that with this guy here, you were interested in knowing the 20th term, and you didn't want to have to keep multiplying by 2 like 20 times. You just wanted to get to the point where you could say, right, well, give me a formula and let me plug in the 20th term, which would be like, you know, way over here somewhere. So if I get to the 20th term, how can I get to that actual number without having to multiply them all out? So this is my first term, second term, third term, fourth, fifth term. How do I get the 20th term without just doubling them every time? Well, we just simply use the formula. This is the formula that generates all the terms in the sequence. So all we need to do is take the information. So the a value, the first value, the first term is 3. So we're just writing that down. So our a value is 3. Our common ratio this time is 2. Positive 2, we're multiplying by positive 2 every time. So the common ratio is 2, and then we just plug those in. So if we want to get to the 20th, then that would be a sub 20. So a sub 20 is going to be 3 times r, which was 2 to the power of 19. Okay, now obviously you would need a calculator to work that out, or I need a calculator certainly. So we're not going to go ahead and do that, but putting that into a calculator would be trivial. It would literally take seconds. It's going to be a lot easier than multiplying by 2 sort of 19 or 20 times. So that's basically how we use the formula, or how we generate the formula, and then how we use the formula to find the particular term that we're interested in. But one thing I want to mention as well is about the general behavior of geometric sequences. Do they converge? Do they diverge? We've got an example of each here. What is our general behavior? For an arithmetic sequence, they always diverge, because if you're always adding a number every time, even if it's a negative, you're either going to get closer and closer to positive infinity, in other words, you're divergent, or closer to negative infinity, so divergent in the other direction. So they're just generally divergent. They cannot converge. They do not have a limit. What about these guys? Well, what is the difference between these two? Well, the general rule is that if your common ratio is more than 1 or less than minus 1, so we would say then that the absolute value of the common ratio is more than 1. So in other words, r has to be strictly greater than 1. So 1.2 or 1.5 or 2 or 5 or 10 or 100, some whole number, then in that case, obviously the numbers are just going to keep getting bigger every time. If you're a number bigger than 1, you're multiplying to a number, you're making that number, you know, just bigger and bigger and bigger. Or if it was a negative, multiplying by like negative 2, then, you know, that's going to have a certain behavior as well. So if the absolute value of r is greater than 1, then that is definitely going to diverge off to infinity. So in that case, there would be no limit. In fact, if you were dealing with a negative value of r, that's actually going to diverge for a different reason, because if you were multiplying here by, for example, minus 2, then it would go 3, negative 6, it would then go 12, negative 24. So that's divergent, but that's divergent because it's alternating. So the numbers are divergent, but also it's an alternating sequence, and an alternating sequence by definition is also divergent. So this one anyway, we can just say is divergent. But there might be a bit of nuance there as to whether it would be a positive or a negative r value, but I'm not too worried about that. What about if the r value was equal to 1? So if the r value was 1, well, that's going to be almost a trivial case, because every term in the sequence would be the same. If you started with 3 and you multiply by 1 every time, you're just going to get 3, 3, 3, 3. So that's pretty trivial. So that, I guess, does have a limit of 3, but that's the trivial case. So that one would converge to whatever the starting value was, whatever the a value was. What about the other case? Well, the other case is this scenario here. That's where the absolute value of r is less than 1. Okay? I might have a look at this one more closely in a moment, because I don't want to confuse anyone, but this is a trivial case. If the absolute value of r is less than 1, so that means that r is a fraction, okay? So r has to be either between 0 and 1, not including 1, or between 0 and minus 1, but not including minus 1. That's the scenario here. So it doesn't matter what your starting value is. If you imagine multiplying some starting value by a fraction and continuing to do that, then you're just going to be getting a smaller and smaller number towards zero. So even if you started off with a huge number, if you're halving it every time, if this is your number and this is zero, you're halving it every time. So you're getting half the way to zero. So it's not going to take you very long to start to converge to zero. And that is true for this general case here. So that is going to converge to zero, okay, like that. Let's actually not worry too much about the nuance with these ones. So that one, if the R value was a negative, then you would have an alternating sequence. The same here actually, if the R value here was a negative, so if we had been dealing here with multiplying by minus 1/2 every time, starting with 10, we would then go down to minus 5, then 2.5, and then minus 1.25, etc. So that's also alternating. So when you're dealing with a geometric sequence, if you've got a negative common ratio, if the R value is negative, it starts to generate this alternating sequence. And by definition, an alternating sequence diverges. So there's maybe a little bit of nuance in the way to write that. But basically, if it's a whole number bigger than 1, it's going to diverge. If it's equal to 1, that's a trivial case, it's going to converge to the starting value, the first term. But the maybe more interesting case is that if it is a fractional ratio, it's going to converge, but not only converge, it's going to converge to zero, because it doesn't matter where you start, even if it was a huge number, if you're dividing it down consistently every time, you'll eventually just get closer and closer to zero, even if you started with a very large negative number. And you can plot that on a graph and actually see how the numbers just get closer and closer to zero. You can see that general trend. So that's basically how we work with geometric sequences. The main takeaway from this class really is what a geometric sequence is, this sort of general definition, and this formula here, which you'll find to be useful. Most questions, at least when you're starting, will be numerical in nature, but later on, if you're doing more work with sequences, they might stay algebraic. So that's why it's good to have a sense for the general form and to use this formula and to know what it means in a general sense, not just with particular numbers. So hopefully that will make sense. There's quite a lot of information in there. They're a little bit beyond the difficulty of an arithmetic sequence. So if you've already done arithmetic sequences and you're happy with those, geometric is a little bit of a step up. So you can check your ability against these guys by working a few practice questions.